Hello and welcome back to my CATIA V5 tutorial series. Today we'll learn how to model a fully parametric internal ring gear. And like the previous video I did about bevel gears, if you haven't seen that you can check it out, we will make sure that it updates automatically to different inputs. This is the gear we're going to be designing, and let me tell you from the start, the internal gear is a little bit more complicated than the bevel gear. The formulas are a bit more difficult, but we will use CATIA's knowledge features to its full extent to make sure we solve this in an easy way. First, we'll create a new part and begin with the parameters. If you don't see the parameters, there's an easy way to fix it. It's in here, the options, infrastructure, part infrastructure, and you make sure these parameters and relations are checked. So first we begin with the parameters. I will fast forward while I input them so you don't have to spend a lot of time watching me write formulas. You can even skip ahead if you like. What is important here is that you use the right parameter type for each thing you calculate. So if the value is supposed to be in millimeters, you use a length parameter. If it's a coefficient, use real. If it's a number of teeth, you can use integer. If it's an angle, use an angle, and so on. It's important for the formulas to work. Okay, now that we're done inputting all our parameters, you notice that I made a little mistake as well. So x1 and x2, which is the profile shift coefficient, has to be a real parameter in order for the formula to work. Otherwise, you'll have to do some strange stuff to make it work. So x1 and x2 is the profile shift coefficient. You see that this is very important while working with internal ring gears, because some of the times they will not mesh properly because of how the geometry looks like, and you need to shift the coefficient a little bit in order to make it work. We also have this alpha W, which is the working pressure angle, and we calculate this by first calculating the involute of the pressure angle, which is calculated like this, very easy with the formula, which I messed up a little bit when I deleted these parameters, but it should be fine. So we calculate this very easily. And for the alpha W, the angle itself, this is where it gets a little tricky, because it's very hard to do using just formulas. And the recommendation for this, when you calculate the gears, is that you look it up in the table, the value for the involute, and then you match it to the correct angle. And that's how you do it. But that's not very parametric, and we don't like to do that. And here in CATIA, we can actually have a better solution than that. We can actually trick it. How do we do that? Well, we plot the involute function, and then we match the value to somewhere in that graph. So we have involute of alpha W here, and here we just need to put some points in. First, we'll have the 0, 0 point. So in order to calculate this, you need the involute function. So this you can create a law here. You see under this table. Click OK. You know the involute function equals tangent of an angle minus the angle itself. And transposing that into the formula editor, it looks something like this. So you have the tangent from an angle minus the angle itself, and this is just to transform it to radians. And what you need to do is to input these parameters here. So you have one parameter of type 2 should be, I guess, length, because we will use this in a point measure length. We call this involute 2, and then we have the angle. Okay, we don't care about that thing, so we have the law 1, which calculates involute. And here we will actually use, this should be on plane, on this plane. We start with 0, and we edit formula here to V. We go to law 1, evaluate, we type here to evaluate, and we need to take this value here, the value of the h. So see, this will be actually the value of the angle we input. We copy this here, we put this 10 degrees, update and see how it looks like. I guess this value is very low, so we might need to multiply it somehow times 1000. Let's see. And we can just copy this point. So let's put 10. That looks much better. Let's try with 20. That looks good as well. 30. Keep in mind that this is the angle, which we don't really need to calculate infinitely. We can just plot it for whatever we want, because you can see it starts to get really steep, really fast, this curve. And now we can just make this curve with a spline like that, just like that. And I guess here, if you look at it, it has kind of like a belly down. We don't want that. We want it to be straight like this. Good. Now we have just plotted the involute law, which is pretty neat, because now we can create a sketch here. We project our involute curve to the sketch, and then we draw a line like this, and we draw a line like this. So make sure this is vertical and this intersects the curve somewhere here. So this actually, our h value is the value for our angle, and this we will actually be having like that. We will make this a reference angle, and this is the value of the involute. This one, the one that we calculated, like that. All right, that looks good. No, yeah, no, this is fine. Yeah. So what we need to do here is convert this to millimeters, actually, because we then get 3.461 millimeters, which is the value in degrees for this involute function. We click OK, and we have this value here. So we have this plotted on our involute function, and this value here should be the value for our angle. So this, even though it's a reference, we leave it like that, and then we go to this one, we add formula, and we go here and we find that length. It was, I guess, this constraint, like that. And this should be just change the we just change the units from millimeters to degrees. And how do we do that? We write something like this. We multiply by 1 degree and divide by 1 millimeter. Now you have your alpha value, which is pretty great. The only problem is, I think this is actually wrong. Alright, so we did a little mistake here. So for this value here, the involute function is not actually an angle, how we wrote. It's supposed to be a real parameter as well. So if you go in here and create a new parameter of type real, and then you just copy the formula. You should have the correct value here. And this one, we can just rename this to involute alpha w2. And I guess we can just replace this parameter with this one. No, it doesn't let us do that. That's unfortunate. We would have to then delete this. Here where we have the involute, we need to link this to the new parameter. Now we don't divide it by degrees anymore, and it's like 0.006, which is very, very low, and that's why it needs 1000. There you go. Now that's perfect. So we are multiplying this by 1000, and we get this here, which is 31.275 millimeters, which actually is an angle. We convert this to an angle here, and there you go. That's how we solve this this angle without having to look it up in the table. Okay, so now that we have our involute graph plotted and we have calculated our alpha, we then need to create a new geometrical set to start designing the profile of our teeth, and we do that by creating a new function, which you do again by clicking this button here. We call this function h, let's say. We start by adding a new parameter of type real, which is going to be called t, and length parameter, which we're going to be calling h. And this is the formula. This is how we write the formula in CATIA, corresponding to the horizontal axis of the involute curve. We have the formulas that look like this, and we will be using h to correspond to how we calculate y in this formula. Parameter rb cannot be used. Okay, so this is actually rb2 because this is what we're using. Now we do the same for the matching axis. We call this v. Parameter of type v length and real t. So we copy this formula here and we change this to RB2 so we don't get any errors again, and we click OK. Okay, now we start by creating a point on this plane, same plane as our function. The h is going to be this one. We write here evaluate 0. Yes, we click OK. This is going to be v. Evaluate 0. That is perfectly fine. We copy this point 5 more times, or if you want to make sure, you can copy it like 7, 8 times, and you start evaluating for different increments. You increment this by 0.1 for each point. So this is going to be 0.2. This is going to be 0.2. 2. Point 3. Point 4. Point 5. I think this is pretty much enough. You then connect them in the order that you drew them, like that, with a spline, and you have your first involute profile for one of the teeth. This is actually one flank of the tooth, and we need to create a second curve for the other side. So we just copy these like that, and here actually you want the V is the height, so you want the height to be the same and the H to be negative. So you have just need to add negative minus here to the first formula. Make sure you don't add other stuff. That's also important too. This is good. This is good. This is good. Right, now what you need to do is to calculate the angle by which you need to rotate this to be able to form the other flank. For the bevel gear, we designed basically a tooth that we patterned around this. For this one, we will design the gap between the teeth. And to do that, we'll need the space width half angle, which is this symbol here, new. And you need to calculate this using this formula. We will create a new parameter. Type angle. We'll just call this n. And again, the way you write this formula is like this in CATIA. Click OK. See how it goes. Yeah, that looks pretty good. Now what you need to do is rotate this around. So there is this rotate. You rotate this. The angle is this parameter that you just added. This is a half angle, so I guess it's 2 times this. The axis is x-axis, and the direction is wrong, so it needs to be minus. So we have our what looks like to be our first tooth. Now you need to draw the circles. Start by, I guess, this the center point. You need to make sure which circles you want to draw. So definitely you need the DF one. So that's RF. This is why we put radius in the first place, because it's easier to link to circles in parameters. So this is RF. Yeah, I guess you can have it half circle. It's easier to split them. So this is the RF, and the inner circle is the DA2. So search for RF2 actually here. Sorry, RA2. RA2. And this is actually what your tooth is going to look like. The exterior diameter of the gear should be actually pretty close to DF2, so it's RF2, and then you're gonna probably add 2 times the module or something like that. This is just a design thing. You can draw it how big you want. Right, and now you need to start joining these together to create the teeth. teeth. So you start by doing this radius here, like that. This is going to be like function of the module. So first thing you notice about this radius here is that firstly you need to trim one of the elements. It's this one, the element 1. And second thing is that you will not fit 2 radii here on the bottom of this tooth. So there's some stuff you can do to fix this. One, you can actually undercut this and make a bigger cutout here. 2, you can change the profile shift of the gear. That'll help you solve it. And 3, you can change the number of teeth. So this difference here is probably not that great. So you can have something like this. You can also reduce the radii here. So this is like 0.2 times the module or something like that. That should be enough. Write the same formula here. You have one part of the cutout. And here I guess it doesn't really matter. You can do it like this. Now you just need to pattern this around. So no, sorry. One other thing you need to do. You need to trim this as well. See how it looks like. Oops, not good. Like that. Yeah, you need to trim this like this. Now you can pattern it. So you pattern it around the X, and you need the complete crown, and you also need the instances equal to the number of teeth. So it's like this. It looks like that. You join this to the original tooth because it doesn't do that automatically. And now you can switch to part design and actually put some thickness into this gear. You can mirror extend like that and have it a function of the module. So let's say 2 times the module. That looks good. This you can have it like 115 mirror extent. And what you also need to do is to cut out the center circle. So to do that, we will use this one. It's related to the DF, and you make it a full circle. And you cut this as well, mirrored extent. Now you can pretty much go into these parameters and change them however you want. So this it can be like 55. So this is what I'm saying about the profile shift. You can change this to whatever you want to update it. Sometimes it will not work. Sometimes it will. It depends on the value that you input. So this is how it looks like with 0.6 profile shift. This can actually be lower. I'm guessing this gear 0.5 was a bit excessive. So 0.25 looks a lot better on this gear, actually. And it should pretty much mesh much better to the other ones. Alright, so now we can go ahead and hide all of this. And I took the liberty to design something off screen. The matching gear of this ring gear to show you how it'll mesh together. So this is designed according to the parameters from this ring gear that we just calculated. This will use the parameters of the D1, Z1, and so on and so forth. And there you go. That's how you design a ring gear. And if you like this video, please leave a like, subscribe to my channel, and hope to see you next time.